Hello, internet friends. Let's we're back with the Z-19 here. Let's pull this logic board and look at it and see how different it is from the one in the DT1 from the previous videos. Yeah. Kind of hard getting in here around the camera. We'll get her though. There we go. That wasn't on there very tight. It's kind of strange. Let's see here. Is this keyed? Yeah, okay. It can only go back on one way. Very good. And these wires here come in the back. This one is also keyed. Very good. And then I guess we just take out these two screws and then the whole thing slides out. Right? I hope I'm doing this right. Yeah, that seems right. Loose, loose, loose. Oh, so that... Okay. Yeah, that stays in there. Alright. Alright. Very good. Oh, we missed a wire. Yes, here's okay, that's just the speaker, so the polarity on it doesn't actually matter. Alright. Now, voila. Alright, let me get rid of this part and we'll take a peek here. Alright, so here's our terminal logic board, and you can see it is a good bit bigger than the one, oh pardon me, a good bit bigger than the one out of the DT1, and I mean, it's almost a general purpose computer. Recall the DT1 used a microcontroller. Well, this thing actually has an honest-to-God Z80 CPU on it. An honest-to-God Z80 CPU. I mean, if it had more RAM and the RAM was addressed, the RAM addresses were decoded correctly, and it could bank the boot ROM out and put RAM, because CPM has to be able to write to the 0 page, and the Z80 begins executing at address 0, so you've got to do some ROM-RAM banking shit to get CPM running. But I mean, you know, this is the same CPU that's found in, like, the TRS-80 Model 2, and here it's just being used in a dumb serial terminal. So that's kind of interesting. Let's see, what else do we have here? Over here is the UART. Now, the DT1 used a UART that was built into the microcontroller. This is actually an 8250 UART, the same that was used in early PCs, and we'll come back to that here in a little bit. This is the display controller. It's, I think, right? Yes, that's the display controller. It's a 6845 compatible chip. And over here is a ROM, a 2K ROM, which I assume is the character ROM, since it's so close to the display controller. Here we have 4 2K x4 RAM chips, and my assumption is that rather than being system RAM accessible by the Z80, that's probably display RAM, because it takes almost 2K to address an 80x25 screen, 80x24 screen. Actually, this does have an 80x25 screen. It has a status line that can be used when you switch it out of VT52 mode and into Zenith mode. but we'll talk about that later. I forgot to mention that in the last video. So you may be wondering, well, why do we have a total of 4 kilobytes then, instead of 2K? Well, you know, each character is a byte, so it'll take 2K to store all of the characters on the screen almost. But then you're also going to have attributes on those characters, like underline and reverse video and shit like that. And I assume that's what the extra RAM's for. Got a couple more ROMs down here. This is the keyboard encoder over here, so I assume that this ROM maps the key matrix to ASCII codes, the same way that the keyboard ROM in the Apple II works. The way the keyboard, I haven't read the documentation for this keyboard encoder, but my assumption is that when you press a certain key on the keyboard, it outputs a certain byte, and then the ROM is used to translate that byte into the actual ASCII code that you're trying to press on the keyboard. That lets you remap the keys in ROM and use a generic keyboard encoder with a variety of different keyboard configurations. I mean, Zenith wouldn't have made this chip. This is just an off-the-shelf keyboard encoder. You know what I'm saying? And then this ROM here is, I assume, the actual, like, system ROM. And there's another socket for a ROM here that's empty, so I don't know what that's for. And up here, there are a pair of 512 by 4 RAMs. So the two of them make 512 bytes altogether, is what I meant to say. And I assume that little tiny RAM is the actual scratchpad RAM that's used by the CPU. So, the 8250 UART, same UART used in early PCs. It derives its clock signal from an external crystal. The only crystal I see on this board is this one over here, so it must be using the same crystal to derive both the serial clock and the CPU clock, which is a little bit unfortunate, because, see, this terminal only goes up to 9600 baud. The main reason I imagine that it can't go beyond 9600 baud is because the interrupt service routine that handles serial input probably isn't fast enough to pull the 8250 in response to the interrupt any faster than that without dropping characters. And that's because the 8250 only has a 1 byte buffer in it. The serial data comes in as a string of bits, and the UART reassembles that into a byte and then puts that byte on an output buffer and generates a hardware interrupt that tells the CPU to branch to an interrupt service routine, and that routine is what will read the byte out of the UART and do something with it. Send it to the display controller or make a bell sound or whatever, right? So the problem is it takes some time for the CPU to do that, and in the meantime, you know, if more than 1 byte comes into the UART, it'll just drop bytes if the CPU hasn't finished that interrupt service routine by the time it's done. So this was also a problem in early PCs. They couldn't go any faster than 9600 baud. The 8250 was later replaced with the 16450 UART, which was pin compatible with the 8250 and allowed a little bit higher speeds. But eventually, the final iteration of this particular UART was the 16550 UART, which had a 16 byte FIFO buffer instead of just a 1 byte buffer, and it was capable of speeds higher than 9600 baud. The 450, not really, but these, you know, they could go up to, you know, like 520 kilobaud, or the 16550 could go up to like 520 kilobaud or something, because it had that buffer which allowed the UART to not drop characters when the CPU was busy handling an interrupt service routine or the delay branching to that interrupt service routine, etc. So the the baud rate of the serial terminal is determined by some setting on these dip switches. It's in the book. I don't have the book open to that page, so I don't know exactly what is what, but it'll go from 50 to 9600 baud, depending on the way you set these dip switches. And since the 8250 derives its serial clock from an external crystal, if it had a separate crystal for that instead of using the same crystal for both the CPU and the UART, my thought was that it might be possible to replace that 8250 with an actual 16550 and then change the serial crystal to something that was double or quadruple the original crystal value, and then, you know, the 9600 baud setting, if you doubled the crystal speed, if you set the machine to 9600 baud with a UART, with a 16550 UART, and it could handle, the interrupt service routine could handle everything fast enough, which I'm still not sure about. It is only a Z80 after all. Then you could theoretically get 19.2K out of the 9600 baud setting, and all of the lower settings would similarly be doubled. If you quadrupled the crystal, you could get 38.4, presumably, out of the 9600 baud setting, and all of the lower settings would also be likewise quadrupled. So if we could do that, we might be able to actually make this into a fairly quick terminal, even though it would still just be a VT52 or the Zenith mode. But aside from the status bar, I can't see any compelling reason to run it in Zenith mode instead of VT52 mode. So, I don't know. We got a couple of possibilities. I mean, the 8250 is socketed, so in theory, we could build an adapter board, a little board that plugged into the 8250 socket that had a 16550 on it with its own clock. And then the system clock would still then only be used for the CPU. That's about the only way I can think of to do it without cutting traces on the board and shit, and I don't want to do that at all. Anything that we do to this has to be 100% reversible. So, yeah, might be interesting to look into anyway. I'll have to look at the schematic in a little more detail. And one thing, so I printed out the manual for this thing, and it's got a list of the ICs in it, but none of the IC numbers on the board match what's in the manual. Very strange. Maybe there was more than one revision of this board and I have the wrong manual. I don't know. Anyway, so the serial terminal that is almost a general purpose computer. If it had more RAM and a disk controller, and you could swap the ROM out for a RAM bank, you could probably run CP/M on the serial terminal. So that's quite a step above the DT1 in terms of processing power. But dip switches instead of configuration from the keyboard, quite a step down in terms of user friendliness and configurability. But it's still a cool machine. And it seems to actually work. So now, next time for real, we'll actually hook a terminal to something and do something more interesting with it than just watching it not do anything like we have been with both of these. Maybe? So, thanks for joining me, and I'll see you next time. Have a blast.